Let's solve this problem. We have moist air at a given temperature of 25 C, 1 atm, and 50% relative humidity. It enters an evaporative cooling unit at steady state. The unit consists of first a heating section followed by a soaked pad evaporative cooler section. So if I would sketch it, I would have it like this. You enter at state 1. You go into a heating section, come out of the heating section at state 2, and then go into this soaked pad evaporative section and come out at state 3. Okay. We're going to be trying to organize information, use a table, talk about the dry bulb temperature at each of those states in degrees C. So it comes in at state 1. I'm kind of put it below 1, and then 2, and then 3 is 25. If you continue to read, the air passes through the heating sections heated to 45 degrees C. All right. And we don't know the exit temperature. That's one of the unknowns. What is in part D? What is the exit temperature at state 3? Okay. But we are given the total pressure in, I'm going to say ATM. We can convert it to kPa, 101.325. And there's no information about it changing, so we're going to assume it's the same kPa, the total pressure going through. Okay. And we are given the information that the relative humidity is 50% at state 1, and then after it's heated it gets to 45 degrees C, and then it passes through that soaked pad, it's back up to 50% relative humidity at state 3. All right. So other pieces of information that we might want to include in here is what is the saturation pressure in kPa for that dry bulb temperature. Well, at 25 degrees C, Psat comes in at 3.169 kPa, and then at 45 degrees C, 9.593 kPa, and since we don't know the dry bulb temperature at 3, we can't do that yet. Okay, so if you take the relative humidity times the saturation pressure, you get the actual vapor pressure in kPa. So 50% of 3.169 is 1.5845, and likewise it's going to be well, we don't know the relative humidity at state 2, so we'll leave it there. All right. At this point, we're filling out the column of information, and we're looking at trying to calculate part A. What's the humidity ratio of the entering moist air? So omega 1, and that's in kilogram of vapor per kilogram of dry air, 0.622 PV over the total pressure minus PV. So we know the total pressure, we just calculated the PV, and you know 0.622, we actually calculate omega. Humidity ratio at state 1, that omega comes in at 0.00988 kPa, not kPa, it's dimensionless. Okay, now if you do a water balance between 1 and 2, you ask yourself, what was the increase in the water content? There was no increase. So omega 2 is equal to omega 1 from water balance. And so it's 0.00988. Okay, then you come back to this equation for omega. It's like I know omega 2 is equal to 0.622. The the partial pressure of water vapor at 2, total minus the partial pressure of the water vapor in the moist air mixture at 2. Only one unknown in this equation is PV2. And when you calculate it, it comes in exactly the same value. It's as if there's no change in the partial pressure of the water vapor because the amount hasn't changed. Its humidity ratio stayed the same. So at this point, you can actually go and calculate the relative humidity at state 2. That'll be the PV divided by the PSAT, both at state 2. And that comes in at 16.5%. All right, that's not one of the unknowns, but it's helpful to know it. And what you see is the relative humidity went down from 1 to 2 simply because you heated it without adding any water vapor to it. All right. So for part B, what is that rate of heat transfer to the moist air passing through that heating section? So I would just do it slowly at the first. You just have this Q dot coming in. And so the energy balance is Q dot is equal to how it's going to change the enthalpy of the dry air. So we have the mass flow rate of the dry air times enthalpy of the dry air exiting minus enthalpy of the dry air inlet. Both of those are dry air. Plus, we have the mass flow rate of the vapor, and then we have what is the vapor enthalpy exiting. That'll be H of G at 2 and H of G at 1. All right. You can divide the whole equation by the mass flow rate of the dry air, and then also change out this change in enthalpy for dry air for specific heat, change in the dry bulk temperature. So this is C sub P of the dry air. And then what do we pick up over here? Mass flow rate of vapor divided by the mass flow rate of dry air, that's omega 1, times H of G at 2 minus H of G at 1. Well, we can put an extra H of G here, and that'll be how many kilojoules per kilogram. And that will be for the saturated vapor. We just look it up in the table. H of G is 2547.2 at 25 degrees C. And 2583.2. So it's like got it. So we can calculate the Q dot divided by the mass flow rate of the dry air. That comes in at 20.46 kilojoules per what? Kilogram of, not dry air. Yeah, that's true, dry air, of dry air. But we look at our problem statement, and they wanted it per amount of moist air mixture. So they wanted it in kilogram, no, right down here. For part B, they wanted it in the rate of passing through the heating section per kilogram of the mixture. So what we have to do is we have to say, well, the mass flow rate of the mixture is the sum of the mass flow rate of the dry air plus the mass flow rate of the vapor in the mixture. All right. So you take and divide by the mass flow rate of the dry air. You'll have the mass flow rate of the mixture divided by the mass flow rate of the dry air is equal to 1 plus the mass flow rate of the vapor divided by the mass flow rate of the dry air, which is omega. This will be at 1. Okay, let me just kind of continue this over here. So if you take the mass flow rate of the mixture divided by the mass flow rate of the dry air for this problem, it's 1.00988. Very close to 1, and most people would neglect that difference. But we're not going to neglect it. We're going to come in here and we're going to calculate Q dot divided by the mass flow rate of the mixture is equal to what we already calculated, Q dot divided by the mass flow rate of the dry air times the mass flow rate of the dry air divided by mass flow rate of the mixture. And so let me just write it out, 20.46 divided by 1.00988, and so finally Q dot divided by the mass flow rate of the mixture comes in at 20.26 kilojoules of energy transfer per kilogram of the mixture, and that's our answer for part B, and there you go. Now, for part C and part D, it's a little bit more work, and they're actually calculated together at the same time. And the best approach, or really the only approach that I know, is to iterate. What do you mean by iterate? Well, guess and iterate and solve two equations and two unknowns. What I'm going to do is scoot down, and we're going to draw a line going across right here. And we're going to say, I need to do a mass balance for the vapor or water, not even do for the vapor. It's a water balance, a water mass balance. Okay, you can focus on doing it just across the pad. So we have coming into the system the omega 1 times mass flow rate of dry air. Okay, that's the water vapor flowing in, plus m dot liquid, that's a liquid water feeding it right down in here in the soaker, and that's equal to omega, this is omega 2, which is the same as omega 1, omega 3 times the mass flow rate of dry air. Okay, so those are our two ends is equal to our flow rate out. So we can manipulate this, or just get that the mass flow rate of the liquid divided by the mass flow rate of the dry air is simply omega 3 minus omega 2, the difference in the humidity ratios. All right. So now the next balance equation is an energy balance. We're going to take the result from the water mass balance and include it into our energy balance equation and get one equation, and then we'll iterate to solve it. But for now, let's just write it out for what does our energy balance equation look like? Well, we're doing this control volume right here between 2 and 3. So we have our mass flow rate of dry air times the enthalpy of the dry air coming in at 2. All right, that's in mass flow rate, bringing with its enthalpy, plus the mass flow rate of vapor. Well, if I do the vapor flowing in at 2, that's just omega 2 times the mass flow rate of dry air. That's our mass flow rate of the vapor coming in at 2 times the enthalpy of G at 2. So the saturated vapor's enthalpy at 2. Then we have one more flow rate in, bringing with its enthalpy. It's our mass flow rate of the liquid coming in, and it's bringing with it the enthalpy of saturated liquid water at whatever temperature. This water for this problem comes in at 25 degrees C. If it came in at 50 degrees C or 45 degrees C or some other temperature, that would affect this enthalpy of the liquid flowing in. All right, those are 3 ins and our only 2 outs. Mass flow rate of the dry air out times the enthalpy of the dry air exiting at 3. And we have how much vapor is leaving. Well, it's omega 3 mass flow rate of the dry air times H of G at 3. That's at 3. So those are our 2 outs. Okay, let's do some combining. If you divide everything by the mass flow rate of dry air, this goes away, this goes away, this becomes mass flow rate of dry air, this goes away, and this goes away. Okay, let's just rewrite that equation. I'm going to have the enthalpy of dry air at 2 minus the enthalpy of dry air at 3. That basically took this term, pushed it over to the other side. Okay, and then we're going to have there's a couple of steps here. Let me just leave it. Omega 2 Hg2, we're going to substitute for this mass flow rate of liquid divided by the mass flow rate of dry air. That becomes omega 3 minus omega 2 times H of F equal to omega 3. Now, seems a little weird, but I'm going to say omega 3 minus omega 2 plus omega 2 all times h of g at 3. I just made it a little, just added and subtracted omega 3. Okay. So what do? Is we take this term and shove it over to that side, and then we take this term and take it over to the other side. Okay, so it doesn't change our change in the enthalpy of the dry air, and we can write that as C sub P of the dry air times temperature 2 minus temperature 3 for the dry air. Okay. Now we're going to come in with omega 2. We're going to have Hg2 minus Hg3. Okay. Equal to H of G3 minus H of F times omega 3 minus omega 2, or you can, either way, that's the way I want to write it so that we can kind of read it. What is this? Well, it's coming in at higher temperature T2 than exiting at T3. So there's a cooling of the dry air. Where does that energy go? Well, it contributes to this term over here. Well, what is this? This is the increase in the humidity ratio, and then the water came in at liquid H of F and left at vapor at state 3. So this is the energy. So this is how much it took to evaporate. So the cooling of the dry air contributes to the evaporation of the liquid water coming in. Okay, but then also there's this one term most of us might skip. We also have the cooling of the vapor. So the vapor came in at H of G of 2 and it leaves at H of G of 3. If you think about it, the vapor came in at, for this problem, the temperature was 45 degrees C, so it has a higher saturated vapor enthalpy, and left at some unknown temperature, T3. This is our unknown temperature, but it's going to be lower than 45 degrees C. So it's like both of these are sensible cooling of dry air and sensible cooling of the water vapor, and it contributes to the evaporation of the liquid water coming in. All right, so this is our energy balance equation. What you have to do is you just guess. What is my exit temperature? Guess T3. Once I have T3, I can compute everything on the left-hand side and everything on the right-hand side, and then I see if they sum together or if it's balanced. If it's not, iterate, change T3. And so after you guess and iterate a few times, you come in with T3 has to be equal to 32.3 degrees C. That satisfies the energy balance equation. All right. And how did you calculate omega 3? Well, I know we substituted in here, but let's take a look. What would omega 3 again be? 0.622 times PV divided by P minus PV, and PV is equal to the relative humidity at 3. This is all at 3. Okay, times P sat at 3. So the saturation pressure is a strong function of the dry bulb temperature, T3. Okay, so it's like once I have a guess at T3, I can get P sat at 3, multiply it by P3, the relative humidity, which was 50% at 3. I can compute omega 3. I can then check to see if this energy balance is satisfied. Okay, so let me scroll up and just say that we do calculate a final dry bulb temperature of 32.3 degrees C, as well as an exit humidity ratio 0.0152, so a lot more humidity than what came in. All right. Well, with that, I want to talk about one other little topic. A lot of people would come down here for this energy balance, and they would say, let's take a look at how much was for our final answers of temperature. It's like the amount of heat associated with this change right here is 12.80. This term, 0.23, they add up to 13.03, and that's equal to the 13.03. Okay, so this does not contribute much. You could neglect it, but in some problems it's not negligible, so don't always just neglect it. This contributes the majority, the cooling of the dry air. Okay. Well, what happens if somebody says, I want to neglect this term right here, H of F is about equal to 0. You can do that. If you did that, let me just scroll down here a little bit. This is a little bit of a digression in the discussion. So if the H of F is approximately 0, then you're not going to get the T3 of 32.3. You'll calculate that T3 is 32.1 degrees C. Now that is not a big difference. That's a very small difference. So that's not a bad approximation to neglect H of F. All right. And then if you did that, then omega 3 comes in at 0.0150 instead of before omega 3 was, what is it I say, 0.0152. So not much of a difference. So this one is also common to neglect. But if you don't neglect it, and in this problem it was coming in at 25 degrees C. I don't know if I gave that value of H of F at 25 degrees C. Let me see if I have that. It's 104.9 kilojoules per kilogram. Okay. And then what about the H of G at, we'll go back and say it's leaving at 32.3 degrees C. Well, that is 2,560.37. So something around 2,560 versus 105. So that's why this is close to being can be neglected. Okay, well with that, we're done with this problem, and hopefully that was helpful.